Let's take a look at different ways to find zeros using division. The first method I'm going to do examples is long division of polynomials. Notice it's set up just like long division is normally set up. And with long division, the two things we have to remember is we are going to multiply, then subtract. Multiply, then subtract. So I'm trying to make my leading coefficients the same. So this is definitely missing a 6, and it's missing a couple of x's. When I multiply this in, I have to multiply it in both parts. That was my multiplication step. Now I subtract. And just like regular long division, I bring down the next term. Again, I'm trying to make my leading coefficients the same. Now I'm missing a 7 and an x. So when I multiply it in here and here, there was my multiplication step. Now I subtract. And I bring down that next term. One more time through, I'm missing a 2. When I multiply here, I get a 2x. Multiply here, a minus 4, and when I subtract, I get a remainder of 0. That remainder tells me that this factor and this factor both go into my cubic. This is what I'm hoping for. If I can get a remainder of 0, I know that I've found a root. Sometimes they're written a little differently, but they all ask for the same thing. They want you to divide. So let's do long division. And keep in mind my two steps, multiplying, subtracting. So I'm making my leading coefficients look the same. Now I'm making these look the same. This time I did not get a 0, so I did not find a linear factor of this polynomial. I have a remainder. They'll write them this way sometimes as well, but there's something hidden in this one. Notice that it is a cubic, but the squared term and the linear term are missing. I have to put those back in. So I need a 0x squared, a 0x for the linear term, and now I have it laid out so I can do long division, making the first terms look the same. When I multiply, that 0 is going to help me keep my placeholder, 0 minus a negative. I bring down that 0. Again, it's just a placeholder. Making my first terms look the same, I need a 2 and an x. I get a 2x minus a 1. And some of you are already seeing this is going to work out nice. Because when I multiply by a 1, I get the exact same thing. That way when I subtract, I have no remainder. So this one also worked out, but notice that we had to put in those placeholders in order to make this work. The last one I'm going to do is very unique to long division, because notice they aren't linear out here anymore. That's okay, we can still do long division even if they're not linear like these are over here. So let's do one more long division. Now I'm still making the first terms look the same, but when I multiply it in, I have to multiply it into all 3 and subtract all 3 of them. Again, I'm making my first terms look the same. All it's missing is a 1. And I'm left with a 1x plus a 1. There's nothing else to bring down, there's nothing else to divide. I got a remainder. Sometimes I will, sometimes I won't. It tells me that I didn't find a factor here, but I can only do this kind of division with something that's nonlinear with long division. I'm going to do those first three problems in a different way. I'm going to use synthetic division. Now, synthetic division is different because we add and then we multiply, whereas long division, we multiplied and then subtracted. So it's a little different, very fundamentally. The nice thing about synthetic division is we're going to take out all the variables. So I'm taking out the coefficients and ignoring the variables. And when I take this linear factor and put it in front, I have to think about what it would be if I actually solved it. So I'm going to put a positive 2 in front instead of a negative 2. So we're going to start out by adding 6, and there's nothing here to add it to, gives me 6. And then I'm going to multiply by 2, add, then multiply, add, then multiply, and then add. Now, you'll see me put this dashed line at the end because this last number is my remainder. So, much like the long division, I found out that I found a linear factor, a root, an answer to this polynomial, but now I need to put my variables back in. We started with a cubic, we took out one factor, so now we must be down to a quadratic. Now if you look back at the long division problem we did, we ended up with the exact same answer. So synthetic division takes out just the numbers, ignores the variables. So we're doing 1, 3, and 5. And remember, we have to change the sign of what we're dividing by. So we're going to divide by a -1. And we are multiplying and adding. Adding and then multiplying. So I'm adding, then I'm multiplying, adding, then multiplying, adding, and this last number is my remainder. We had a quadratic. We took out one of the factors, so now we're down to something that is linear. Much like long division, when we go to do this problem, we have to put in our placeholders. So this is a cubic. We're missing the quadratic term and the linear term and the constant term. And now when we take this out, and if you can't see it, do a quick calculation of making it a 0. It looks like we're supposed to take out 1/2. So that's what I'm going to put in my little box. And now we'll do the synthetic division. Adding, then multiplying, adding, then multiplying, adding, then multiplying, adding. This is our remainder. So we found a factor, we found a root, an answer to this. We went from a cubic back to a quadratic. So x cubed minus 1 breaks down into 2x minus 1 and 8x squared plus 4x plus 2. So what we're demonstrating with both of these methods is this idea of, do we have an answer? Do we have a linear factor for our polynomial? Another way you can do the exact same thing is what's called the remainder theorem. Now we looked at the remainder both in synthetic and long division, but now they're going to have us look at it just a little differently. Notice I've got the same problem up here again. That I'm supposed to divide by x minus 2, and we found out earlier that this would only work if x is 2. So I'm going to plug a 2 in everywhere I see an x. Now I definitely have some arithmetic to do here, but when I multiply this all out and then add and subtract, I get 0. That's my remainder. So knowing I got a remainder of 0 tells me that this factor works. Let's look at the one that didn't work. If I plug in a -1 everywhere I see an x, and I add this up, I get 3. That's the remainder. That tells me that this factor does not work because I had a remainder. Same remainder I would have gotten doing synthetic division or earlier with long division.